Hi, welcome to the Tectonic Laboratory at the University of Bern. My name is Frank Zwaan. I'm a postdoc here. I'm working together with Guido Scheures and Timmy Schmidt in a project focused on rifting. What you see here is a machine that we use for our models. The idea of these models is that we try to reproduce plate tectonics and especially rifting. If you look in nature, rifting and plate tectonics in general takes long time, so something like millions of years. This is something we cannot observe, so the dynamics remain difficult to understand, and therefore we build models like here in Bern with simple materials in short time spans to better understand the processes going on. This specific machine here has been designed by engineers from Rapperswil. It has various motors, various axes that can move in all kinds of directions, allowing a lot of different setups for our models. We also have a second machine, which is over there. And this machine is also designed by the people in Rapperswil, and it allows a rotational kind of extension or compression, which is something special, and it's really exciting. Okay, so what you see here is just a quick example of one of these models. So this is a rifting model. You see here nice graben structures. The idea is that we have a brittle viscous model where the viscous material, which is silicon like this, reproduces the lower crust, and we have then a layer of sand on top, which is the upper crust, which is then brittle and creates these beautiful structures here. The idea in this model is that we have a base plate here, a plastic sheet, which has an angle of 30 degrees, and then this sidewall here is being moved in this direction, creating these en echelon oblique structures. You just saw a nice model in the laboratory. However, these models take a couple of hours to develop, so it's difficult to really show the deformation in real life. Therefore, we have a couple of analysis techniques which I would like to show you. The first step would be to take top view pictures of the model and compile these into a time-lapse video, which then shows you how the model is developing over time. The next step is to quantify deformation, which we can do by means of 2D pattern tracing analysis in collaboration with the GFZ in Potsdam. And if we then play the video, you will see that we get nice vectors and colors showing how this model is behaving. So far I've shown you 2D examples of model analysis, but we would also like to go into 3D. So our PhD student Timothy Schmidt has installed a camera rig where we have multiple cameras at different angles, which allow us to recreate the surface and also to calculate deformation in the model. This is a topography analysis. If we play the video, we can see which parts of the model are moving up and down. 3D particle analysis also allows us to really follow where faults are developing. So for instance, here we see the propagation of faults. And we can also trace this in a diagram like here, so we can really quantify what's going on inside our model. The next step is that we can use the CT scanner from the University of Bern Forensic Department in order to analyze and monitor the internal structures that develop within the model. The CT data allows us to create 3D visualizations of our models. For instance, this model here creates a rift in the center and creates conjugate fault sets. And this one here creates just a central rift in the center of the model. But this is not all. We really would like to see what's going on the inside of the model. This is a brittle viscous model where we have sand and a viscous layer. And if we start deforming this, the weak spot that we put in the model starts deforming, creating a nice, beautiful rift. We can not only show you a nice video depicting the internal structures developing, but we can also start calculating and tracing displacement in these models and deformation in these models by means of digital volume correlation in collaboration with Royal Holloway, University of London. So this digital volume correlation can be used to really quantify deformation in 3D within the model. So not just horizontal in section, vertical in section, but also vertical out of section, really in 3D. The things I've shown you so far are really quite unique, especially this easy access to a CT scanner means that we can do really exciting analysis of our models. And our laboratory is really at the forefront of analog modeling innovation. This is something we're really proud of. But I would like to finish by showing you this traditional cross-section of a recent rift model we did in collaboration with the University of Strasbourg. The idea is that you wet the sand, then you can cut the sand in order to reveal the internal structures. And these can be quite complex, as you can see in this section. And this is actually the way that people normally make their sections. It's quite fun to do, and we're also happy to do this here in Bern.